Many thanks for giving this opportunity. Today, I would like to speak about some stability results for the Lorenz attractor. This is a joint work with Wael Baksoon and EM Melbourne. I mean, yeah, okay, it's working. So we all have seen the Lorenz equation, and many works have already been done regarding this system, like it admits an SRB measure, which is unique. For example, it's in the paper of Araujo, Pacifico, Puas, and Viana. And the SRB measure mixes at exponential speed. That's work of Araujo and Melbourne. Also, the flow itself and its time one map satisfies many limit theorems, such as central limit theorem. That's in the work of Mark Holland and Ian Melbourne, and its time one maps also satisfy CLT and almost sure invariance principle and other limit theorems. That's the work of Araujo, Melbourne, and Varandas. So, well, what else we would like to study is kind of a perturbative results, stability results. Like suppose that you perturb the flow and get a close flow to the initial one, and suppose that it admits an SRB measure or reasonable invariant measure, and then is it continuous with respect to this perturbation? So when epsilon converges to 0, does the invariant measure of perturbed flow converge to the converge to the invariant measure of the unperturbed flow? So that's what I mean by this convergence. Or since we have said that the flow satisfies central limit theorem, if you fix a Holder observable, then there is a corresponding variance to this. And naturally, this variance depends on the observable and also on the flow through its invariant measure. Then is this variance continuous with respect to the perturbation? I mean, there are other natural questions. For example, here we are studying the continuity of the measure, but one can study the smoothness. Well, here also one can study smoothness of the variance. As in the case of ANOSO flows, such a works exist, but let me stick with these two types of questions. Actually, one of them, because the statistical stability, the first question was answered in our work with Wael Baksoon, and for geometric Lorenz flows by Alves and Sophie. So today I would like to concentrate on the continuity of the variance in the central limit theorem. Well, as we all have already seen many times, we derive the statistical properties through the geometric properties of the flow or the geometric properties of the underlying system. And therefore, let us define this kind of structure, a geometric structure that is that will be useful, that we will use. So here I would like to be a little bit general, but the actual Lorenz flow is contained in this class of systems that I will describe now. So let G be a C2 vector field and X be its associated flow. Assume that G has a unique fixed point and the linearization, the derivative at the singular point has 3 real eigenvalues. So as you can see, 2 of them are negative, 1 is positive, and if they satisfy these conditions, then we call them Lorenz-like singularity, just because the original Lorenz system has this property. Now, so usually you take a cross section. This is a surface, or yeah, in 2-dimensional cross section. to the flow, and then you define the return map. So assume that there exists a well-defined Poincaré map from sigma to itself. So because we have this singularity x0, there will be one stable for manifold in gamma, which will never come back. It just collapses to the fixed point as time goes to infinity. That's why I have defined the Poincaré map from sigma minus gamma to sigma. Well, assume that the flow is singularly hyperbolic. That means there exists stable foliation that consists of C2 stable curves, and in the transversal direction it is C1 plus alpha. So, and assume that the stable foliation is exponentially contracting. I think one can consider weaker contracting rates also, but for our purposes, it's I think for our technique to work, it's important. So now, of course, now I have a cross section foliated with stable manifolds, and it's natural to take the cross section, the quotient map defined on some interval, on a compact interval, and obtained by quotienting along the stable curves. So you get a one-dimensional map, and we assume that this one-dimensional map is transitive, and because the stable foliation is C1 plus alpha, I directly get the one-dimensional map to be C1 plus alpha, and yeah, so that's the property. But I'm assuming these boundary points, the xi0 to go to boundary points. This is the intersection of I with the singular stable manifold. Now, it is known, we assume also that the one-dimensional map obtained in this way is uniformly expanding. So you have now a kind of a reduction from flow to one-dimensional uniformly expanding C1 plus alpha map, which has a singular point. And therefore one can apply the known spectral techniques, functional analytic approach to this one-dimensional map and lift it to the flow. So this is our approach. And that's why I've defined all those. And I would like to know that then that this, what have the system, the family of flows that I've described includes the classical Lorenz flow by the results of Warwick-Tucker and Araujo Melbourne results. So Tucker proved the existence of the Lorenz attractor topologically, and then the C1 plus alpha stable foliation was proved in the paper of Araujo and Melbourne. Well, this is what I've been describing. So you have the flow and the cross section here. As you flow along the line, it comes back. As you can see here, this gamma collapses to the singular point. So now I'm ready to state the results. Suppose that I have a family of flows as described above with the properties that I've just described, and the singularity at some point x epsilon. Now let us define this technical norm. So it's L1 norm plus the L infinity norm of the observable. Then we have a theorem, let C and C prime be two Hölder observables. Well, actually for the first result, I don't need this, but yeah, this is the statistical stability, and I need phi psi to be Holder continuous starting from B and C. So as epsilon goes to 0, the variance of the perturbed flow converges to the variance of unperturbed one, and it has this kind of estimate. So is kind of so it's nice to see this estimate because as you see here, you have the norm of the observable psi. So this is the main result, and it appeared in Annals of Henri Poincaré this year. Let me also try to sketch the proof of this result. As I have already told you, the idea is now to use the previous geometric structure. So first, we take a cross section and reduce the flow to a Poincaré map, and then to a one-dimensional map. Now we study the one-dimensional map. It has CLT, it has exponential decay of correlation, and also strong stability results on the spectrum of the one-dimensional map. But the problem is to lift these results to the flow back, because the return time will have a singularity, and this is the main, this causes many difficulties in lifting the results proved for one-dimensional map to the flow. So first of all, as usual, we make change of coordinates and rectify everything, or trivialize the stable foliation. So we can choose a system of coordinates so that in this system of coordinates, the Poincaré map has a skew product form, and well, this has been proved for Holder for Lorenz system, and the return time for the perturbed flow has logarithmic singularity at 0, or at the singularity of the flow. Now, so we can write the return time in two parts. One part is that takes from that's the part where the flow goes nearby the singularity, and that's the part with the logarithmic singularity for the return time. But the second part is, it starts from you start counting from outside of some neighborhood of the origin, and then the T2 epsilon is a uniformly Holder continuous. I mean, it is Holder continuous, and the constants can be chosen independent of epsilon. So we also can ensure that the contraction rate along the stable direction remains uniform in epsilon, and then define observable kind of observables for the mu flow. So by this equality, we can see that if I define f epsilon by this formula, then the distribution with respect to the pushed forward measure mu tilde epsilon and mu epsilon are the same, so variance should be the same. So by making change of coordinates, we haven't changed the variance in the central limit theorem. That's why I'm doing this here. Now, so the idea is, as I've already told, to reduce to the Poincaré map first. But to do that, you define this induced observable. You take integral along the flow up to time tau epsilon. Well, because tau epsilon has singularity, even though you've started with Holder observable, the capital psi would be an unbounded observable. But we are subtracting the value at 0, so psi tilde epsilon is 0 at 0. So as you approach the origin, psi tilde goes to 0, and there is some hopes that we can control the Holder norm of first of all to make psi epsilon bounded, and then control its Holder norm. Actually, this psi epsilon will be piecewise Holder. Now there is a relation between the variance of the suspension flow or the flow and its Poincare map when you have the return time function tau. So we use this formula, and the first step is to show that the integral of tau epsilon, the return time with respect to the invariant measure of the Poincare map, converges to the unperturbed integral, and then then we try to prove the same thing for the variance. Well, for this we use the Green-Kubo formula, and notice that the flow is exponentially mixing, so I can use the Green-Kubo formula. Well, the rest is more or less technical computation, but what we do, we still use some anisotropic norms in order to show that the Poincare map is exponentially mixing, and then then the sum converges, and this sum converges, and then we lift the statistical stability to the this class of observables that are piecewise continuous, and some technical estimates allow us to conclude that the variance of the perturbed flow converges to the variance of the unperturbed one. Yeah, I think this is all I wanted to speak about.